Connors. I'm Quinn.
I'm David.
And I'm Connor.
And we're here to talk about the empirical gas laws today. Instead of Mr. Craig, because he's super lazy.
Alright, these are the 3 empirical gas laws we're going to be talking about today. And this is all in ideal gas situations. And I'm going to be talking about Boyle's law. For Boyle's laws to work, moles and temperature are constant. And as it says, pressure is inversely related to volume. So as volume decreases, pressure increases, or vice versa. And this is because as volume decreases, there's going to be more confined space. And the more confined space, the molecules are more tightly packed and will hit the walls more often than it used to, creating more pressure in the confined space.
Our second law we're going to be talking about today is Charles' law, which is appropriate because my name is Charles. So as you can read here, Charles' law states that as the temperature increases, the volume also increases, as long as the container that the gases are in is expandable. So as you can see from this visualization, the particles as they heat up move a lot faster and collide with much more force against their container, creating a larger space for them to expand into. Now, if you look at the gas here, you can see how volume and temperature are directly related, as you can see. So as this is our temperature in Celsius and our volume in milliliters, and it increase is a gradual constant slope. Also, for Charles' laws to work, the pressure and the moles of the gas have to be held at a constant.
I'll be talking about Avogadro's law. Here we can see that the number of moles and the volume are directly related to each other. As the number of moles increases, the volume increases, and vice versa. It could be represented by Avogadro's law equation, where this is volume, this is your constant that relates the two, and this is your number of moles. If you double the number of moles, the volume will also double, because since there are more particles, it takes up more space. We're assuming that pressure and temperature are always constant. And this is the gas that you use is irrelevant, since 1 mole of oxygen and 1 mole of helium will be the same amount of particles.
Oh, why hello there! I'm Professor Charles, and I'm here to talk to you about my law, Charles' law. So, for this experiment, we'll have the beloved whoopee cushion and an open flame, or as I like to call it, a snap of the fingers. So as we have our flame here, we'll place the whoopee cushion above the flame and wait for a period of time for the balloon to expand. And voila! Our balloon has expanded because the heat from the flame has caused the particles inside of the whoopee cushion to move more quickly and expand the rubber whoopee cushion.
We are adding moles of air, and as you can see, the volume is increasing.
Now let's show Boyle's law. For Boyle's law, as I push in, I'm giving the molecules less space to go, creating more pressure in the ball. And if I push hard enough, theoretically, the ball would explode because there's too much pressure for this material to hold. Oh, hello there. Okay, for this lab, you're going to need a graduated cylinder, in this case, measuring cup. You're going to need soda can. You're going to need an ice bath. You're going to need a hot plate, which is a stove. You're going to need water, the sink. You're going to need a tong, and you're going to need a timer, which is the phone.
And eye protection.
Oh, yes.
First, drink the Coke as to not be wasteful. Then, to measure the volume of the Coke, fill it with water, and pour the water into the graduated cylinder. Now, we have the volume of the Coke can. Okay, so you want to measure out 5 milliliters of water. We're only going to do it once, but you should do it multiple times at varying increments, like 5, 10, 15, 20, 25 milliliters. And then you want to pour your 5 milliliters into the Coke can, and then take your Coke can over to the hot plate or stove.
Before we begin this, we want to make sure that we have our eye protection on because flames are very dangerous. Okay, so now that we have our flame ignited, we're going to place the can atop the flame until we see the water boiling inside of the can. Alright, so now that the can has been on the stove for a while, you'll begin to see a little bit of whitish smoke. That's the water vapor from the boiling water. And we're going to time a minute from when we first saw the white, and then we're going to flip it into our ice water. We waited a minute and we're ready to flip.
No, do it quickly.
3, 2,
Quick.
1. So after the can has been crushed, we're going to refill the can with water to measure the volume, and then empty it into this glass container. And we're going to measure it and see how much the volume has changed.
Alright, so this is our setup with just water and just regular air filling up the rest of the can. But when we boil the water vapor, which is going to expand to roughly 600 times its liquid volume, is going to push out the air and fill it up, which is Charles' law. So as the volume of the water vapor increases, it is directly proportional to the heat increasing as well.
When we flip the can over into the ice bath, the drop in temperature causes the water to change states from gas to a liquid, which in turn causes its volume to decrease, as denoted by Charles' law. Here, because the volume has decreased so much inside the can, there's a vacuum, so there's a very low pressure zone in the can and a high pressure zone outside. And due to Boyle's law, in order to equalize the pressure of the can has to increase, but to do that, the volume of the can must decrease, so that's why it crushes.
Alright, so now I'm going to explain why the can crushes instead of the vacuum force pulling the water from the bottom. So the can is made of aluminum, which is a very weak metal, which means that it requires less force to crush than simply pulling the water up into filling the space and equalizing the pressure inside and outside of the can. If the can was made out of a stronger material like steel or any other strong metal, then the water would simply just be sucked up because it's much harder to collapse that steel.
Instead of using Boyle's, Charles, and Avogadro's laws, you can use some derivations, physics that Dr. May can teach you to come up with the ideal gas law, which relates all the variables for you into one nice equation. But of course, this only works for ideal gases, which is almost never.
I want to thank you guys for watching our video.